Welcome back again, everybody. We are going to start in this video with the bridge from Module 1 going into Module 2. We're going to need to look at relationships between multiple variables, specifically covariance, correlation, and the slope of a regression line in order to get there. And I'm going to do that with a slight modification of our favorite toy example here. Look, it's the Transformers data once again, but you see I've got the original 7 people and their heights, and I've added a column with their weights. Now, of course, you expect people who are taller to weigh more. And all of the lingering story about what was going on in this data set is still there. You see our last observation here, Optimus Prime, is not only very tall, but he weighs as much as a couple of cars here. So the outlier is still in play, and we can still make all of the same general stories once we jump into looking at the relationship between these. But the idea is the individuals in this data set who are taller also weigh more. The individuals who weigh more also are taller. Over here on the right, I've got a couple of boxes built in. So single variable statistics for x, and I'm going to call height x. You could call height h. That would make perfect sense. But x and y are kind of the standard letters that we use for an independent and a dependent variable. We tend to model y as if it's a function of x, whether that's the case or not. Generally, in real business world data, you might be looking at variables that influence each other, or it may be obvious which one of them is causal and which one is sort of the effect. But that's a sticky topic. X and Y over here, you can consider calculating the mean of X, the mean of Y, the variance of X, the variance of Y, the standard deviation of each of these. And the mean, variance, and standard deviation of X we've already done in a previous video. The mean, variance, and standard deviation of Y may be something interesting, and it's worth talking about the units. So the real quick review here is, of course, the mean of X equal to average of all of this data has the exact same units as the original data. The average person in this sample of 8 individuals, including a giant robot, is 89.125 inches tall. Well, how much do they weigh? Let's find out. The average person in this sample is going to weigh, and these are meant to be pounds, is going to weigh about 2,000 pounds. The average person weighs about a ton because, of course, there's a very large individual. When we do variance here, again, variance is going to come with 2 different flavors, a population formula and a sample formula. We do want to use the sample formula, so let's do that. The variance for x, using these 8 observations, close those parentheses, 35, 31, a number you'll remember from the last round of looking at all of these. And the standard deviation is, of course, the square root of the variance. So I could say this is SQRT, parentheses, and click on the variance. In this time, I'm not going to do that. I'm going to switch it up and say ST DEV, sure enough, standard deviation is also in there. So I'll go ahead and take the standard deviation of a sample, this one, the second one here, and I'll use that. Looking at the original 8 observations over here, close those parentheses, and I should get a number that I recognize, and I do, 59.4269. Okay, well, let's grab the variance of the weights. RS of these data, and just for fun, okay, a very large number. Once again, variance is going to be differently scaled numbers. That's what this last column is for. And let's grab the standard deviation. Standard deviation of these. What do I infer from these numbers? Well, units are inches here, inches squared in the variance column, which kind of doesn't play nice, and then inches again. So inches with a question mark, because variance column is maybe a little bit of not playing well with others. For weight, this is supposed to be pounds, so I'll write that there. But the point I'm trying to make is this enormous number is actually square pounds, so square inches. And sadly, yes, square pounds. In the case of variance, square pounds don't make any sense, and square inches as a measure of height don't make any sense. So as we discussed in the previous video, the mean and the standard deviation go together very nicely, and from those we can make cool things like z-scores, or t-statistics, which we haven't quite gotten to yet, and so on and so forth. Confidence intervals, mean and standard deviation will do that for you. The same kind of story is going to live here when we build in multivariate statistics, specifically bivariate relationships. Right now, I want to look at correlation, the slope of an OLS regression line. Sorry, I said correlation already. Correlation, the slope of an OLS regression line, and covariance. And the units of these are very important, even though all of them hinge on these two variables here. So I'll tab back to the whiteboard, and I'll start defining things. I'm going to start this paradigm, which is kind of our path to Module 2, with covariance of two variables. So note, right off at the top, with the rainbow pen, I've got x, comma, y, two random variables. So RVs. Very nice, RVs. So covariance of x with y. If you want to know how these things are formally defined, this is still a sort of average, and I'll use notation that we didn't use in the previous video. I'll say, by the way, something like x bar, where I say the sum of all the xi over n, this is just an average, and this is kind of like the population average, which we usually call mu, and then define as the expected value of x, where this letter E means expectation, or expected value, or average in this case. Well, it's the same thing here. So the expected value of x is just the average. So here's our sample. I've actually got some data. I'll add them up, divide by how many there were. That's the average. It's the expected value of x. So this notation is doing that work for me. Covariance is, again, a type of moment, but it's a co-moment. It's an expected value of two things being related in a certain way. You'll recognize it, especially in relation to variance, which I'm going to say variance of x. Again, the sample version of this, which we called s squared, is the sum of all the xi minus x bar. Throw some parentheses around those, square them, and divide by how many there were, minus 1. It does have a degrees of freedom correction built in there, but translating that, what is this? It's basically, let's go ahead and use the weak equals. This is our stand-in, our sample counterpart to sigma squared. That's a 2, I promise. Which is the expected value of x minus mu squared. Okay, mu being the true average, this one up here, population. So the squiggle is saying this thing I have in a sample is kind of like this thing I have in the population. Sample over here, population over there. Sample over here, and population over there. Fine, Greek letters, Latin letters, not that interesting. Well, covariance is going to play the same game. It's going to look a lot like this. In fact, almost exactly the same in one special case. What is it? Covariance in a sample is going to be the sum of all the xi minus x bar, okay, so far so good, times yi minus y bar. Okay, fair enough. I've got x's and I've got y's. Where are they? Well, here are my x's, x1, x2, x3, x4. Here are my y's, y1, y2, y3, y4. Multiple observations of each of these variables. And then I'll divide by n minus 1, just like with the regular variance. Notice what's happening here. This is not variance in the sense I had up here. This is a measure of how these variables co-vary. So when x is above average, let's swap colors. When x is above average, I'm going to have a positive number here for xi minus x bar. Fair enough. When y is above average, I'm going to have a positive number here for yi minus y bar. Now think about the relationship between x and y. Like in the case here where I'm talking about the height and the weight of these people, if x is above average at the same time as y is above average, then I'll have a positive number on the left and a positive number on the right. But if x and y are above average at the same time, that seems to imply that they're below average at the same time. And I'm generalizing here. So if they're usually above average at the same time, then they're usually below average at the same time, meaning I'd have a negative number over here and a negative number over there, but negative multiplied by negative brings back a positive number. All of that to say, covariance measures how these things vary together. Positive number means that these things do in fact vary together, and a negative number means that these things vary in opposite directions. X is usually larger than average when y is smaller than average, and vice versa. Okay, well, what else can I say about the formula I'm looking at? Xi minus x bar has units of x, yi minus y bar has units of y. Interesting. Okay, so a couple of things to say about it. Units of x times units of y. And I'll say that as x dot y. Interesting. Are these numbers going to be large or are they going to be small? Well, it depends on the original units and it depends on the amount of variation in the original data. We also have some names for these things, like with variance. We had s squared for the sample variance, and here this sample covariance, you can tell it's in a sample because I put a hat on the name covariance. I'll come back over here and I'll say sample covariance. We've also got a name for that. We'll call it SXY. S meaning something like variance or standard deviation, but XY referring to the fact that there's an X and a Y. This is the one that has both of them covariance. The other simple thing here is, of course, I noticed that covariance of X with X instead of Y is the sum of all the X, again, with a hat, the sample counterpart to the population statistic is xi minus x bar, hang on, that's an x bar, times xi minus x bar. Oh, it's the same variable twice. Well then, I'm going to go ahead and simplify that and just call it squared divided by n minus 1, and you'll recognize that immediately as the variance of x estimator, which we call, of course, s squared. It was right here. Same guy. Okay, so I've got covariance. There is one special case of covariance where it's the covariance of x with itself, and that's just variance. Otherwise, it's going to tell me something about the relationship between two variables. Let's have a look. I'm pretty sure Excel can handle one of these, and I've got an interim column here. So I'm going to do something clever, and I'm going to say I've got the averages of both of these. I could do xi minus x bar, I could do yi minus y bar, and I could make a column of xi's minus x bar multiplied by yi minus y bar. It's a bit excessive to do all of that, but it won't hurt doing it just once. So let's say xi minus x bar, yi minus y bar, and let's say, parentheses, xi minus x bar, yi minus y bar. I did drop the subscript over here just to save a tiny little bit of horizontal space. But let's do it. So what will it be? Xi in this case is 64, and I want to subtract from that 89.125. Can't resist that urge to just type in the number and click and drag down. Yi minus y bar in this case is equal to yi, 115, minus I've got a little bit more going on with the decimal places over here, so okay, it's just 6 digits, but I went ahead and clicked on it and grabbed it that way. And I'll tell it to freeze those before I click and drag down to there. There's yi minus y bar. Just like xi minus x bar, I noticed that 7 of these observations are below average, and one of them is quite a lot above average. So I'm seeing the same story with the height and the weight, and I'm starting to think that these things do in fact covary, or that the correlation between them could be high. We haven't gotten to correlation yet, but we're going to need it here in a second. Now, the product of these two, xi minus x bar, yi minus y bar, that multiplied by that is equal to that number. Click and drag it on down. So, the covariance is going to be the sum of all of those divided by n minus 1. Let's see, equals sum of all of these divided by 7. 330, 710. Okay, all right. Well, I'll come over here and grab an extra cell and say is equal to, does Excel have a function for covariance? And of course it does. No surprise, it has 2 of them. Covariance.p is going to divide by n, and covariance.s is going to divide by s, just like the variance and standard deviation that we've already looked at and tried out. So I'm not going to do both of those for comparison. It works, as you would expect. I'm going to go ahead and grab covariance s and say the covariance of, let's see, oh, it asks for 2 arrays. First variable, then the second variable. Gotcha. Well, I'll grab the first variable here, and then I'll grab the second variable there, and then I'll close the parentheses, and I will hope and pray that I get a number like 330.710.0893. And I'm very happy because the covariance in Excel did, in fact, calculate the exact same number. I'll grab that number, bring it up here, and say the covariance is that number right there. All right. And the box that I've already labeled in shaded yellow asks, what are the units? The units on covariance are units of x multiplied by units of y. This is why we have perhaps a bit of a struggle with whether we want to use this thing. Units of x times y. In this case, that is inch pounds, which sounds like a unit of work, or it sounds like something a bit more exotic in a physics sense than inches or pounds or anything that would have to do with the relationship between inches and pounds. I'm not sure if I do want to use inch pounds here, but that's what it is. Inch times pounds. All right. Well, that's what it is. And what about the scale of these numbers? Well, this is going to be on the order of magnitude, usually, something like the standard deviation multiplied by that standard deviation. You've got some big numbers, and you've got some other big numbers, so you multiply them together, and you're going to wind up with larger numbers in accordance with the size of the numbers that went into the formula to begin with. I don't know what inch pounds mean here, and I don't know what 330/710 means, except I notice that it's positive. So covariance is usually interpreted in terms of its sign, telling you whether the relationship is a positive correlation or a negative correlation. But if we're talking about correlation already, then we're skipping to the next step. What is correlation? Well, correlation is a much friendlier version of covariance. Covariance, in the usual setting, is only really used as a stepping stone to one of these other 2 statistics that mean so much more to us. Covariance gives us correlation, and it gives us the slope of an OLS regression line. Both of those are very useful. So let's do correlation. Sticking for a moment with the rainbow pen, or this, whatever you call that. It's not exactly a rainbow, but I'm going with it. So, correlation between x and y. Sure enough, this is going to have, and I'll put a hat on it because this is a sample, it's going to have a cool name. We usually call this guy rho. Sometimes we call it R. So I'll stick with the convention and say R, X, Y, instead of rho. Rho being a Greek letter, I'll save that for the population correlation, which perhaps wouldn't have a hat on it, but all of that is the notation. What do I do for this thing? Well, it's going to be covariance of X and Y, the sample version, divided by the standard deviation of X, and then the standard deviation, let's fix that, of Y. All right. Again, easy formula. Notice what happens. The covariance of X and Y, if we want to keep hats on everything, let's make the notation work here. And if we want to give those names, if we want to give those names that we may recognize based on their the letters that we use to refer to these guys, that's SXY, the covariance, divided by S, the standard deviation, and I'll give it a subscript X because I have a standard deviation of X and one of Y now, and then divide by S again, but I'll give it a subscript of Y because it's the standard deviation of Y. Look at the units. Units here are units of X times units of Y. Then I divide by something with units of X, then I divide by something with units of Y. And putting these three circles together, I make some sort of a joke about State Farm Insurance, call or click for a quote today. But what do I see? I see units of X times Y, star, units of X times Y divided by X, then divided by Y, and I notice what that means. No units. Capital I with a dot. That's kind of a nice day. Correlation, you may already know, is always between -1 and +1. In the case where covariance is negative and these things move in opposite directions, I can get correlation that is also negative. Standard deviation will always be positive. And remember what I said just a moment ago. Covariance is usually going to be something on the order of magnitude that you would get when you multiply standard deviation of X by standard deviation of Y. And if it's not smaller than that, you have two variables that move a lot together. So if I have a correlation close to 1 or close to -1, then I have two variables that are very highly dependent on each other, or should we say, correlated. However, covariance can be very small if X and Y don't tend to move together, or if they are, let's say, close to independent, or they don't seem to have correlation, in which case the covariance could be as close to 0 as you want it to be. Back to here, that 330. I told you we usually interpret this in terms of the sign. I see that it's positive and these things are correlated with each other. As it turns out, when I compare that to these standard deviation numbers, this is going to be large. But covariance could be positive or negative. The other thing it could be is close to 0. But like with z-scores, close to 0 doesn't mean much if I don't understand anything about the size of the units I'm working with. I need to know how close it is to 0, and how close it is to 0 is going to be relative to the variation in the original data, which is standard deviations. So let's go ahead and calculate a correlation for these two variables, X and Y. What do I have to do? Well, I've got covariance right here, and I have standard deviations up there. So I'm going to go ahead and use this cell right here as a little scratch paper. I'll say this one is equal to my covariance. In fact, you know what? Let's use the covariance that's in the box up here. Covariance divided by parentheses that standard deviation and then that standard deviation. So I've got something with units of X and Y divided by something with units of X and divide it by something with units of y. Hit enter. Sure enough, extremely high correlation, almost equal to 1, 0.99896. The highest correlation can ever be is 1. The lowest it can ever be is -1. And somewhere like 0 would be close to no relation between these variables in a linear dependence type sense. Okay, this is great. Units? No units. Unitless, unit free. I call that a good day. Well, correlation is something you probably already know, and covariance is just a unitified version of correlation, which is actually one of the building blocks in order to get to correlation in the first place. But if I went back to here and I saw my x and my y and I really started asking questions, then I might be, would I dare to look at a scatter plot of these things and see how strongly they depend on each other? My goodness, that does look like, okay, all right. Yep, that seems like it could be strong dependence. So, add trend line. Interesting. There's your trend line. We're going to have to figure out where that trend line comes from and what the slope of that is going to be like. So, I'm going to hang on to that for just a second. Bring it down here and forget about it for a minute. Back to the whiteboard. The last piece of this puzzle is not covariance or correlation, but actually something that uses the exact same information as both of these. It's the slope of the regression line I just looked at. We've got a name for that. This one's going to be called beta hat. It's beta 1 hat. And I can use whatever color pen you like here, which is OLS slope. And the formula looks like this. So follow along. In the numerator, I'm going to have the sum of all the xi minus x bar times yi minus y bar. And in the denominator, I'm going to have the sum of all the xi minus x bar squared. This is how the formula is typically represented. If you want to unpack what it is and understand where it comes from in relation to the other two that we have in this cute paradigm right here, three things that make sense together, look at the formula and we'll break it up into a couple of pieces. So this top piece in the numerator looks an awful lot like covariance. It is the formula for covariance, but it's been multiplied by n minus 1. So I'm going to go ahead and rewrite it just very slightly and say this is equal to 1 over n minus 1, the sum of all the xi minus x bar, yi minus y bar. If I do it like that, this is covariance. And then what do I have in the numerator? Of course, dividing the denominator. Dividing the numerator by 1 over n minus 1 means that I'm going to need to divide the denominator by 1 over n minus 1. Let's go ahead and do that. N minus 1 in the denominator just to make sure that all these numbers are still the same. Sum of all the xi minus x bar squared. And I see that, yeah, sure enough, that is covariance of x with y divided by the variance of x by itself. And I'll put hats on these just to remind myself that it's the sample version of both of those. In a previous video, I mentioned that there was a special case where this n minus 1 degrees of freedom correction that shows up in variance and gets inherited by standard deviation because it shows up in variance, and then shows up again in covariance. There is a special case where it doesn't matter. And you see it illustrated here in the OLS slope because it wouldn't matter whether I was dividing by n minus 1 or dividing by n. if I use the sample covariance or the population covariance in Excel, as long as I use the variance that matches for the denominator, I'll get the same answer for the OLS slope. So that's actually kind of very handy. The n minus 1 versus n doesn't matter for the OLS slope. And I would remark that if you take that idea up to here and try it out in correlation, you'll see that the exact same thing is true, because I've got standard deviation of x over here and standard deviation of y over here, which is the square root of the variance of x and the square root of the variance of y. So sure enough, it doesn't matter whether you divide by n or n minus 1 to use the sample formula or the population formula when you're building correlation, as long as you do it uniformly. Make all three of these use the same rule. It'll cancel out just like it does here. The n minus 1 cancels out in the numerator and the denominator to give you something that looks like this. So it wouldn't matter whether you had used n or just n minus 1 or just n. That's very nice. Okay, also, covariance of x with y divided by the variance of x, you might look at that and say, that's a bit like covariance of x with y divided by the square root of variance of x, and then the square root of variance of x again, which of course is just an elementary splitting the variance into its own square root multiplied by its own square root. Why would I do that? Because I noticed that that's not just variance, that's the standard deviation. SD of x, and then the standard deviation of x again. And I'll give this thing one more name in reference to correlation. Correlation is the covariance of x and y divided by the standard deviation of x, and then the standard deviation of y. If I take that and say that's correlation of x with y multiplied by a fraction, the standard deviation of y over the standard deviation of x. Why would you do this? So that I can get to the end of the line and draw another star and say units of y divided by units of x. Notice I have here units of x, units of y, and then I divide by units of x twice. So the units of y don't get canceled out, and there's an extra units of x in the denominator. Or, if you want to do it the long way, then I have correlation, which is unitless, multiplied by the standard deviation of y, which is units of y in the numerator, and then divided by the standard deviation of x, which has units of x in the denominator. Why does that matter? Because we need to go back to the picture where this thing came from, the slope of a regression line. Well, let's draw some axes. This is x down here. This is y up here. And there's a scatter plot. There are a bunch of dots floating in space. Now, the scatter plot that I just saw in Excel was a bit uglier than this one. This one's sort of idealized. I'd like the data to be laid out in a cute tube like this, where I could just fit a line right down the middle and talk about, without regard to the fact that it's starting to curve at the end. So fit a line right down the middle of the data. Magical. And talk about the shape of that line in relation to these axes. If I did just a slightly better job this time, how about that? We'll go with it. I've given myself a line that doesn't look like it's going through the origin, because I'm going to need this intercept right there. The intercept is going to be called beta 0. Of course, the estimated version of that would have a hat. And tracing along the line, I remember that the slope of a line is given by rise over run. So A, B, draw this nice right triangle focused on the line. Use a different color if you want to emphasize that it's not part of the line. This is A, this is B, and A over B, rise over run, is going to be what we call beta 1 hat. I'll use the slope and the intercept, this guy and this guy, to come over here and define a line, which, to be frank, I might as well just put up here. So I'll say yi hat is equal to beta 0 hat plus beta 1 hat xi. You'll recognize this from regular geometry as essentially slope-intercept form, where we would say y is equal to mx plus b, slope-intercept. But the slope here is beta 1, and then the intercept is, of course, beta 0. So it's like intercept-slope form. It's a bit backwards, but we can make it work. Now, what is this going to do for us? Every point in this picture gives us a little bit of information about the relationship between x and y. The line generalizes that information to a big picture, where it says, yeah, on average, x and y are related in a particular way. The idea of stretching the sample average, which we call mu, or x bar, and turning it into something like a line instead of just a single number is a cool idea, and that's called regression, and that's what all of Module 2 is about. But it works using least squares. So ordinary least squares works this way. We'll start to build it. I imagine that there is a line that fits through this data, and I imagine that it can be expressed in a way like this, where my estimated line gives me a prediction for each observation. Of course, I plug in a value for x and say, I think xi is here. Well, then I trace that up to the line and I say yi hat is there, according to the vertical axis. Fair enough. Every value of x you can put in gives me a prediction for y. That's useful on its own. But the beta 0 and the beta 1 may tell you a story like each additional year of education corresponds to a certain amount of change in your expected income, if there is, in fact, correlation between education and earnings or income, which you know that there is. So I'll go back to here, hit Control-Z a few more times, and erase some more of that. Clean up my mess. And I'll explain how we build this. Each point, there's your data, there's your information. Each point has a specific vertical distance from the line, which I'm going to illustrate using cute little curly brackets here. See how far that is? See how far that is? Draw that little dotted line. Say, yep, it was that far. And that vertical distance I'll call epsilon I. So for this particular observation, which is a Cartesian pair xi, comma, yi, epsilon I is the distance between yi and yi hat. Yi hat was this point down here, right? Yi hat. And the difference between what actually happens and what the model predicted is the error term, which I will call epsilon. And epsilon, of course, can also have a hat, or it can be replaced by a Latin character. Very often you'll see people do this with a lowercase e in place of epsilon. I'm used to epsilon for whatever reason. So you go through and you say, what should be true about these epsilons if the model was good? Epsilons should be as small as possible. I want this line, wherever it is, to be as close as possible to the data. So the line should not be, say, here. Well, that's, first of all, it's going the wrong direction, and it's a little bit too far down and to the left, so that's probably a lousy line. It shouldn't be here. It's too flat and it's too high up, and it shouldn't be here. That's way over there to the right. I want it as close to the data as possible, and I want epsilons to be as small as possible. That leads me to something like the average. epsilon. I say the sum of all the epsilon i's from my fitted model should be small. Epsilon, though, is sometimes positive and sometimes negative. And you know what? There was another negative one over here where this point was well below the line. Look, another, and another, and another one. So instead of minimizing regular epsilons, I might think about minimizing the absolute value of epsilons added together, but that's not easy to do with calculus because absolute value is not a strictly convex function. So I'll do something similar to what we did with the variance. I'll square them, and I'll minimize that in order to come up with beta 0 and beta 1 xi. We've got a name for this, by the way. This is the sum of squared residuals. Or SSR. The residuals are easy because it's these epsilons. They're the error terms. They're the leftover pieces. So epsilon is a residual or an error, and this is frequently called the sum of squared errors, just like it's called SSR. Or, so I'll say SSR or SSE, meaning errors. The sum of squared errors is one of my favorite statistics. It fits into a class of statistics that have the name of the statistic is the formula for the statistic. And it's great to work with that sort of statistics because I can give it to you on something like an exam or a homework assignment. You should be able to remember how to do it every single time. It's the sum of these squared residuals. So what do? You take the residuals, you square them, and you add them up, thus creating the sum of squared residuals. There's also the mean squared residual, which you would infer is going to be the average of the squared residuals, so I guess I'd have to write a little 1 over n in front of the sum in order to make this the average, which it now is. I'll call that the MSE, mean squared error, or MSR. Medium speed rail, mean squared residual. This is usually called the mean squared error, but that's not where we're going. In order to minimize the sum of squared residuals using calculus and solve for beta 0 and beta 1, I'll go ahead and write each epsilon as a function of beta 0 and beta 1. Remember, epsilon is the distance between the yi here and the yi hat. So if epsilon I hat is the difference between what actually happened and what the model predicted, yi hat is just beta 0 plus beta 1 xi. So I'll go ahead and plug that in where it needs to go, which is here. So it sounds like epsilon I, which will get a hat, is yi minus beta 0 hat minus beta 1 hat xi. Okay, let's talk about minimizing the sum of squared residuals here. SSR is equal to sum of all the epsilon I hat. It's going to be we're going to put hats on these once I find the numbers that we're going to use. They don't have to start with hats. I can imagine a world where there's an epsilon for every beta you might choose. Every beta 0 produces a certain type of epsilon. Every beta 1 produces a certain type of epsilon. So I'll do a version of this with no hats for just a bit until I figure out what those beta 0 and beta 1s are. I think we all agree I could draw a line here and then find a different set of epsilons, right? That line doesn't look very good, so I presume that that's not going to be the solution to the problem. Sum of squared residuals will be the sum of all the epsilons squared, which is the sum of all the yi minus beta 0 minus beta 1 xi. Throw some parentheses around that and square that. And then I will say my rule is this. Beta 1 hat and beta 0 hat minimize the SSR. This is ordinary least squares. It's called ordinary for some reason because everybody does it pretty much all the time, and it's called least squares because I'm taking the squared error terms and I want them to be as small as possible because I want the line to be as close to the data as it can be. So let's minimize the sum of squared residuals using calculus in order to identify beta 0 and beta 1 that will be the solutions. Well, if you know how to do this, we basically have a paraboloid here. It's like a bunch of parabolas. Each of these is a parabola. There are many of them added together, and they're not regular parabolas. They each have two variables in them that I want to minimize with respect to. So I'll have two first-order conditions. It will go like this. Take the partial of the SSR with respect to beta 0, and then take the partial of the SSR with respect to beta 1. And if you've never taken calculus, don't worry about it too much. I'll show you how this works. So the partial with respect to beta 0, I look up here and I can't explain all of calculus, but I know the simple steps at least. Taking the derivative of the sum of squared residuals doesn't care about the sum at all. It's just going to be the sum of the derivatives of these other parts. And then I know that the 2 comes down in front of the parentheses first because I'm going to use the power rule. And then I have to multiply that by the derivative of whatever was in the parentheses. So a couple of steps here. 2 goes down in front. Let's see. Sum of all the 2 parentheses yi minus beta 0 minus beta 1 xi, close the parentheses, and then multiply by the derivative of what was in the parentheses, which is the chain rule. That's just the derivative of this expression with respect to beta 0 is simply minus 1. So it is in fact negative the sum of 2 times all of those things. And the first order condition says that this has to be equal to 0. Okay, I do that again for the partial derivative with respect to beta 1. Again, looking at the sum of all of these, I take the derivative of the parentheses first, the 2 goes down in front, then I multiply by the derivative of whatever is happening inside the parentheses with respect to beta 1, which is going to be negative xi. I wind up with negative the sum of all the 2 xi parentheses yi minus beta 0 minus beta 1 xi is equal to 0. I have two first order conditions. I have two equations. Notice that they're just about linear in two unknowns. And I think I can solve this. I'm going to start with the first one. It looks like the place to go. I'm going to notice that if this is equal to 0, then I don't think the 2 matters. I'm just going to ignore the 2. And the same thing happens down here. If this whole thing is equal to 0, then the 2 doesn't matter. In fact, the minus doesn't matter. So the 2's and the minuses are going to vanish immediately. And I'm going to jump in with this and say, okay, well, if all of those added up are 0, let me write it out that way. The first order condition, sum of all the yi minus beta 0 minus beta 1 xi, these still have parentheses, equal to 0. Now, I could write that as many sums instead of just one sum and say the sum of all the yi's minus the sum of all the beta 0's, this is going to be fun, minus the sum of all the beta 0 xi is equal to 0. The sum of all the yi's is the total of the yi's. It's not going to do much for me, but I do recognize a couple of pieces I think I could manipulate. Because this is all equal to 0, I could divide both sides of the equation by n, and I'm going to. I'm going to write a little 1 over n in front of each of these. And I'm going to write a little 1 over n next to the 0 just to have a laugh. Of course, it won't do anything. But I notice that that first term is now y bar, the average of y. I noticed that the second term, how many beta 0's were there? Well, there's a beta 0 for every observation in the data set, which means n of them. And if I add up n of something, This is fun. So beta 0 plus beta 0 plus dot 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 beta 0 n times is literally the definition of multiplication, is n times beta 0. And when I say it's the definition, I mean it. That is the textbook definition of multiplication. So adding up n of beta 0 here is n beta 0. This is 1 over n times n beta 0, which is just beta 0. And then what do I have over here? Well, I've got a typo, first of all. That's a beta 1, not a beta 0. So let's fix it and say that's beta 1. And I also noticed that the beta 1 could come outside the sum, and then that's going to be, just like with the y bar, that's going to be beta 1 x bar. All of this leaves me, eraser, all of this leaves me with y bar minus beta 0 minus beta 1 x bar is equal to 0. And I'll spin that around to say, ergo beta 0 is equal to y bar minus beta 1 x bar. And I think I have a solution for beta 0. So what I'm going to do is I'm going to take this almost solution for beta 0 and I'm going to plug it into the other equation. Since I had two first order conditions, I'm going to have to pick up that equation right there and bring it down here along with what I just derived, where beta 0 is y bar minus beta 1 x bar. All right, so here we are. Noticing that the 2 doesn't matter and the minus doesn't matter, I'm going to go ahead and have the xi times everything else being equal to 0. The sum of all the xi times yi minus beta 0 minus beta 1 x bar, sorry, not yet, that's still xi, is equal to 0. But you see, I wanted to do something there. I wanted to go ahead and take this and drop it in right there where I've got a beta 0. Now what's that going to give me? The sum of all the xi, parentheses, yi is still yi. Beta 0 becomes y bar minus beta 1 x bar. So I have y minus y bar minus, well, it's going to have two negatives, so it's going to be minus beta 1 x bar. I'm going to write it as minus beta 1 xi from here, and then I'm going to say plus beta 1 x bar equals 0. Then I'm going to break that into two pieces. I'm going to say that's essentially the sum of all the xi, yi minus y bar minus beta 1, because everything else has a beta 1 in it, sum of all the xi minus x bar. Interesting. Well, that's equal to 0. What can I do with it? I can do a couple of cute tricks. I'll try one. So right here, right next to that xi on the left, I'm going to add something. Actually, I'm going to subtract something. I'm going to subtract the sum of all the x bar yi minus y bar. And if you're thinking, you can't do that, you can't just subtract things out of nowhere, you're correct. But there's something special about this term, which is it's 0. Because the yi's and the y bars add up to the same number. Remember, y bar is the sum of all the yi's divided by n, and there are n of them here. So in fact, this thing is 0. That's a cute proof. You're welcome to try it. I'm going to do the same thing over here. I'm going to not subtract. Oh, I'm going to add beta 1 times x bar. Now over here, this x bar can be outside the summation because it doesn't vary with I, so you can write that either way. I'm going to write it the other way over here. X bar times the sum of all the xi minus x bar. Why would I do that? Because, once again, that's actually 0. The sum of all the xi minus x bar is 0, and the rest of this is just a constant times 0. So I can do that, and it does tend to make things a bit cuter. So I'm going to wind up with the sum of all the xi minus x bar times yi minus y bar. And then for this other term over here, I'll say minus beta 1, the sum of all the xi minus x bar times xi minus x bar. What will I do with that? This is all equal to 0, so I'll add this term to both sides and say beta 1, sum of all the xi minus x bar squared, since I just realized these are the same thing twice. Okay, well, I'll just square it and don't bother writing it twice, is equal to the sum of all the xi minus x bar times yi minus y bar. Do you see the last step? Ultimately, what I get from this exercise is beta 1 hat, the one that solves the equation, is the sum of all the xi minus x bar yi minus y bar divided by the sum of all the xi minus x bar squared, which is what we had a moment ago and is in fact the covariance of x with y divided by the variance of x. Sample versions of those. Why the proof? Because I didn't motivate the proof from this expression. I motivated the proof from the starting point of making the error terms as small as possible. I motivated the proof from the idea that I just want a line that fits the data as well as it possibly can in terms of being close to the data. It turns out, in fact, that this line that has that slope and a formula for an intercept, which we may have already forgotten, but there it is, that's the intercept. So put a hat on that one, and that'll be what we, and put a hat on that one. There you go. Now we've really solved it. I've got a formula for a slope and an intercept of that line that I can actually prove are going to give me the line that is closest to the data in terms of something pretty simple, the squared error terms. A couple other magical things come out of this, where, for instance, here, I had another name for this. This is the sum of all the error terms. So you might look at it and say, that's just your first order condition. And yeah, it is, but we also called this the sum of all the yi minus yi hat, or the sum of all the epsilon I hat. That's 0 according to the first order condition from the calculus. Well, if that's 0, then I could draw a little 1 over n and say the error terms are 0 on average. The error terms are not only as small as they can possibly be in this model, they're 0 on average. Some of them are positive, some of them are negative, and the line is going to go right through the center. So this line is a beautiful mathematical representation of the average of y for each value of x in the form of a line. What else can I say about it? Well, we've already figured out that it's very closely related to correlation, and covariance, more or less, came along for the ride. If you like, and you don't know where covariance really came from, you can treat that proof of where the OLS coefficient comes from as a nice starting point for where covariance comes from. It's just the numerator for either of these. And if you want the OLS slope in terms of rise over run, we can do that and have units of y divided by units of x. But if you want the same information in a unitless fashion, of course, we can also do that and have correlation. Well, Module 2 is all about using OLS, and there's quite a lot more to say about that tool. So, quickly, I'll pop back to here. I'll remind myself that, yeah, I was able to fit a line to this data, and if I click on it, Format Trend Line, Display Equation on Chart, I do have the option to go ahead and have Excel just tell me what the line is. Why is it, here's my beta 1, and here's my beta 0. So, that's that. And I'll throw it out and say 93. The slope is something like 93. Let me see if I can calculate that myself, since I think we have all the tools we need. I've got the covariance. I've got the variance of x, which is right here. So let's see. OLS slope should be equal to the covariance divided by the variance of x. Wish me luck. This needs to be something like 93. We got lucky. The slope is 93. So on average, for each additional inch of height, the people in this sample weigh 93 more pounds. That's a lot more than the relationship between height and weight for regular people, but one of these people is a giant robot from space. So it makes sense. And the last way that I might want to do this, go back over here where I can see the data again. Let me go up to data analysis. There it is, regression. So it's in the analysis tool pack, and it will do quite a lot more than just the slope and the intercept. Let's go ahead and highlight the y range, which is these 8 observations. Let's go ahead and highlight the x range, which is these 8 numbers. I don't have labels. A new worksheet is perfectly fine. I don't need residuals. Let's hit OK. And Excel will give me this regression output. Now, we're going to spend some time in Module 2, and hopefully by the end of class, by the end of this half a semester, everything in this table will make sense to you. And we can add a few options as well. But for now, I'll just look through and say, there's my intercept, and there's the slope of the line with respect to x that we just saw on the graph, and what I just derived using a little bit of calculus. The rest of these, like r squared, adjusted r squared, multiple r, you might recognize that as the correlation, and of course 8 observations I think you'll be able to recognize as a number that you do know from this data set. The rest we will put together step by step, starting in Module 2. So I'll end this video. That concludes everything for Module 1 and a bit of Module 2 that we've already started into.